Welcome back to our unit on reactions in stoichiometry. This is the first of two videos on Learning Goal 5.2. This video will cover the first two success criteria A and B. Our 5.2 learning goal: I understand the limits of chemical reactions, and the two success criteria that will be covered on this particular lesson are success criteria A: I can define and determine the limiting reactant in a reaction, and success criteria B: I can determine the mass of the excess reactant remaining in a reaction. So let's look at a scenario that will help us understand the idea of limiting reactants in chemical reactions. The question is, how many sandwiches? Kind of seems like an odd question to ask, but I want you to consider this scenario. So you're going to make some ham sandwiches for a party. Each sandwich will use 2 slices of bread, 1 ounce of ham, and 0.75 tablespoons of mayonnaise. So when you gather your supplies, you find that you have the following. You have 13 slices of bread, 5 ounces of ham, and 20 tablespoons of mayonnaise. The question is, how many sandwiches can you make from those ingredients? Well, if you think about it, the answer would be 5 sandwiches, and here's why. Once you make your 5 sandwiches, you have at that point run out of ham. Because notice, every sandwich will contain 1 ounce of ham, and you have 5 ounces. So once you get to 5 sandwiches, you have no more ham left. You can't make any more sandwiches. In other words, the reaction, in this case the making of the sandwiches, must stop once any one of the reactants runs out. So once any one of these reactants, the bread, the ham, or the mayonnaise run out, the reaction must stop. And that is the case with any chemical reaction. Once you run out of any of the reactants, whether there's 1 reactant or 10 or however many there are, the reaction is over. So in this case, we would call the ham limiting. So it is limiting in this scenario, and thus it determines how many sandwiches are made. In other words, it wouldn't matter how much more bread or how much more mayonnaise we had. If we only have 5 ounces of ham, I could only make 5 sandwiches. Even if I had 1,000 slices of bread and 1,000,000 tablespoons of mayonnaise, I could only make 5 sandwiches with 5 ounces of ham. Thus, we will have bread and mayonnaise left over. So let's see how this applies to an actual chemical reaction. So first, a definition. A limiting reactant is the reactant that is completely consumed in a reaction. It will determine the amount of product that can form. This limiting reactant is determined by mole-to-mole ratios in a balanced equation. An excess reactant, this would be any reactant that is not completely consumed in a reaction. In other words, there will be some left over once the limiting reactant is all consumed. So let's look at how we actually determine a limiting reactant in an actual chemical reaction. So recall this. The limiting reactant is the reactant that runs out first. In other words, it can produce the least amount of product. So let's look at this reaction. In the formation of water, 4.0 grams of H2 are reacted with 64 grams of O2, which reactant is limiting. So here is the equation for the reaction, and note it is already balanced. Just like every other stoichiometry problem, we must have a balanced equation to start with. So here's how we determine which reactant is limiting. It's not simply look at which of these is the lower number. So I cannot look at the 4 grams and the 64 grams and say, well, hydrogen's limiting because there's less of it. It might be limiting, but it's not because there is a smaller mass. Because recognize that reactions occur on a mole ratio basis, 2 moles of hydrogen to every 1 mole of oxygen, not on a mass basis. So what we will do is we'll calculate the amount of product that each reactant could form if it all reacts. So in other words, I want to know what mass of water, how many grams of H2O am I going to get if all 4 grams of H2 react. So this is just a gram, mole, mole, gram problem that we've already learned how to do with stoichiometry. So I'm going to convert my mass of hydrogen to moles using the molar mass. Notice grams of hydrogen cancel. Now I'll use my mole to mole ratio. Note 2 moles of hydrogen to every 2 moles of water, and moles of H2 cancel. Now I can go from moles of water to grams of water, where moles of water cancel using the molar mass of H2O, and that will give me 36 grams of water. So what did I just calculate? Well, here's what I know. If all 4 grams of hydrogen react, I don't know if it will or not yet, because I don't know what the limiting reactant is, but if it all reacts, 36 grams of water can be produced. So that's my note here. If all 4 grams of hydrogen react, 36 grams of water can be produced. We now need to do the same thing for the oxygen. We need to see how much water that can produce if it all reacts. So the same thing we did before, a gram, mole, mole, gram. I want to know how much water we can produce from the 64 grams of oxygen. So just like before, it's a gram, mole, mole, gram. I use the molar mass of O2. Grams of O2 cancel. I can now use the mole to mole ratio. Notice it is 2 moles of water to 1 mole of oxygen. So moles of O2 cancel. Now I can use the molar mass of water like I did before, and that will give me 72 grams of water. So what did I learn here? If all 64 grams of oxygen react, that means 72 grams of water can be produced. So we are now in a position to say what our limiting reactant is. I have this on the next slide here. So here's what we just said. We just calculated if all 4 grams of hydrogen react, 36 grams of water can be produced. If all 64 grams of oxygen react, 72 grams of water can be produced. So ask yourself, which is going to run out first? Is it going to be the hydrogen or is it going to be the oxygen? Well, the hydrogen can produce less water. Once we get to 36 grams of water, there's no hydrogen left. It all reacted. So that tells us the hydrogen, the H2, is the limiting reactant. So H2 is limiting. Again, the reason is once we get to that 36 grams of water, all the hydrogen has run out. There will still be oxygen left over because I can see the oxygen could produce 72 grams if it was allowed to run out. So what mass of water could we produce then from this reaction? Well, the answer is 36 grams because once we get to 36 grams, there's no hydrogen left. So the reaction's over. It stops. All right, along this same idea here, we also want to be able to figure out how much of the excess reactant would be left over, or how much of it would remain once the reaction stops. So we're going to look at the same reaction again, the formation of water, where we react 4 grams of hydrogen with 64 grams of oxygen. We already know hydrogen is limiting, that's from the previous calculation. So we want to determine the mass of the excess that's left over. Well, if hydrogen's limiting, that means oxygen is in excess. It will be left over in the end. So if I want to know how much remains, I need to know how much reacted. I know I had 64 grams at the start. If I want to know how much is left over, I need to know what mass of oxygen reacted with this 4 grams of hydrogen. So this is just going to be another gram, mole, mole, gram problem. I want to know what mass of O2, my excess reactant, will react with my limiting reactant of 4 grams of hydrogen. So notice, once you figure out what the limiting reactant is, in this case it's hydrogen, the entire stoichiometry of the problem is based on that limiting reactant. I know all 4 grams of hydrogen will react because it's limiting, so I will use that to figure out how much oxygen is going to react along with it. So again, this is just a gram, mole, mole, gram problem. I convert to moles of hydrogen using the molar mass. Then I use my mole to mole ratio for the balanced chemical equation. Then I use the molar mass of oxygen, and we get 32 grams of O2 reacted. Note, this is not the answer to the question. This is the mass that reacted because it's 4 grams of hydrogen that react. If I want to figure out how much is left over, I now have to subtract that from the initial amount. Now, yes, in this case, we do end up with the same number. That's just happenstance here. We had 64 grams of oxygen at the start, 32 grams reacted, so I will be left over with 32 grams at the end. Again, this is a very rare circumstance. Typically, this would not happen because typically we don't react exactly half of any excess reactant. All right, so let's put this all together and look at a different sort of problem. I shouldn't say different sort, same sort of problem, just a different reaction, different numbers. So let's consider this reaction. Phosphorus reacted with oxygen to form tetraphosphorus dicoxide, P4O10. So again, you can see we have a balanced chemical equation. We know the importance of starting with a balanced equation. Always make sure the equation is balanced before starting. So here's the question. If 25.0 grams of phosphorus and 50.0 grams of oxygen are reacted, what mass of tetraphosphorus dicoxide is produced? So I want to know what mass of this is produced from my reactants. 25 grams of the phosphorus, 50 grams of the oxygen. Here's the thing we have to do. Even though the question doesn't tell us to, we must determine the limiting reactant to know how much product we can make. Because I don't know which of these is going to run out first. Again, I can't simply just look at the numbers and say, oh, there's less phosphorus, so that will run out first. I have to do the calculation, figure out which one will produce the least amount of my product. That will tell me what my limiting reactant is. So again, these are just gram, mole, mole, gram problems. I want to know what mass of product, how many grams of P4O10 are going to be produced if all 25 grams of phosphorus react. So again, just using a gram, mole, mole, gram calculation, convert my grams of P4 to moles of P4. Now I use the mole to mole ratio of 1 to 1. Now I can go from moles to grams of my P4O10, and that will give me 57.3 grams of the P4O10. Now again, what this tells me is if all of this reacts, I don't know if it will yet, but if it does all react, all 25 grams of P4, I will get 57.3 grams of my product, P4O10. I now need to do the same thing for the other reactant, for the oxygen. I want to know what mass of product, P4O10, we will get if all 50 grams of oxygen react. So once again, it's just a gram, mole, mole, gram problem. I use the molar mass to convert from grams to moles. I use my mole to mole ratio, this time 5 to 1, moles of oxygen to moles of P4O10. And then I can use my molar mass to convert from moles to grams. And I can see here, this is 88.7 grams of the P4O10. So here's what I know. The oxygen will produce more of my product if it all reacts. So the oxygen is going to be in excess. It will not run out. The phosphorus, the 25 grams of P4, will run out because it will produce less of my product. So the answer here, at least part of it, even though we weren't asked this specifically, the P4 is limiting because it produces the least amount of product if it all reacts. So from this, I can answer the question. I don't need to do any other calculation. We're asked what mass of P4O10 is produced. Well, that's the 57.3 grams that I calculated here. Because once I get to that 57.3 grams, all of the phosphorus is now used up. So 57.3 grams of P4O10 can be produced. Continuing with this same reaction and the same masses, I now want to know what mass of excess reactant remains. So again, the exact same reaction, we have the same mass of the reactants that we had before, same problem. Now I just want to know how much of the oxygen is left over. I know it's oxygen that's left over because phosphorus was the limiting reactant. So remember what we need to do here. If I want to know how much is left over, I need to calculate how much of it reacted first. So I'm going to use my limiting reactant, my 25 grams of P4, and I'm going to see how much O2 reacts along with that. So again, just another gram, mole, mole, gram problem. Convert from grams to moles. Use your mole to mole ratio, 5 to 1, moles of oxygen to moles of phosphorus. Then you can use the molar mass, and that will tell us that 32.3 grams of oxygen reacted. Well, if 32.3 grams of oxygen reacted, I can subtract that from my initial mass of 50 grams, and that will give me 17.7 grams of O2 remaining. All right, one more practice problem, and I'd like you to pause the video once I get this pulled up here and try this on your own. Once you've tried it on your own, give it a play, see how you did, and make any corrections as necessary. All right, so here's the question. Get it all pulled up for you here. So once you've read through this, you can pause it and give it a shot. So consider this reaction. We have sodium bicarbonate, the NaHCO3, reacting with hydrochloric acid, HCl, and we get these products here, sodium chloride, water, and carbon dioxide. So we're told 1.82 grams of hydrochloric acid are reacted with 2.01 grams of sodium bicarbonate. We're asked three things. A, determine the limiting reactant. B, what mass of carbon dioxide is produced. And C, calculate the mass of the excess reactant remaining. Well, this is the first time we've seen multiple products, so that you might have the question of, well, if I want to determine the limiting reactant, which product do I use in my calculation? Frankly, it doesn't matter. You can use any of them, but I would read all the questions. Notice here, question B asks you what mass of CO2 is produced. So I'm going to figure out how much carbon dioxide my hydrochloric acid can produce, how much carbon dioxide my sodium bicarbonate can produce. I'll see which one of those will produce less. That will tell me the limiting reactant. At the same time, it will also tell me how much carbon dioxide I can get. So that's what I'll do. So I want to know how many grams of CO2 can be produced from 1.82 grams of hydrochloric acid. Again, just another gram, mole, gram. Hopefully you're seeing the common theme here. Grams of HCl will cancel, converting from grams to moles. Now I use my mole-to-mole ratio, 1 to 1. Do notice this equation is already balanced. This happens to be an equation where there's just 1 mole of everything, so it makes it pretty straightforward. Now I can use my molar mass, and this tells me 2.20 grams of carbon dioxide will be produced if all of my hydrochloric acid reacts. Again, I don't know that it will yet because I don't know what the limiting reactant is. Now I'll do the same thing with my other reactant, my sodium bicarbonate. I want to figure out how much CO2 will be produced if all 2.01 grams of sodium bicarbonate react. So using my molar mass, converting from grams to moles, now I use my mole-to-mole ratio, 1 to 1. Now I can use my molar mass of CO2, and that will give me 1.05 grams of carbon dioxide. So I'm now in a position where I can answer both of these first two questions. Notice the sodium bicarbonate will produce less carbon dioxide if it all reacts than the hydrochloric acid. So that tells me the sodium bicarbonate, NaHCO3, is limiting. It also tells me how much CO2 can be produced. That would be the 1.05 grams. Because once I get to 1.05 grams, I'm out of sodium bicarbonate. My reaction stops. So lastly, I need to calculate the mass of excess reactant remaining. Well, that's my hydrochloric acid. But in order to know how much is left over, I have to know how much reacted. So again, I will do another gram, mole, gram. I want to know what mass of HCl is going to be reacted with my 2.01 grams of my limiting reactant, the sodium bicarbonate. So doing my gram, mole, gram, converting grams to moles, then going moles to moles, and then moles back to grams using the molar mass. That will tell me 0.872 grams of HCl reacted. And now I can subtract that from the initial amount of 1.82 grams of HCl, and that will tell me that 0.95 grams of HCl are left over. So I've answered the question. Sodium bicarbonate is my limiting reactant. It will produce 1.05 grams of carbon dioxide, and I will have 0.95 grams of the HCl remaining. All right, so giving a quick overview now again of our success criteria and learning goal. So this video, we started to look at understanding the limits of chemical reactions, and we defined and determined limiting reactants from a reaction. And we also were able to determine the mass of the excess reactant remaining in a chemical reaction.